In March 2016, Google DeepMind's AlphaGo shocked the world by beating a human champion at the complex board game. Go is considered to be one of the hardest games for computers to master because of its immense complexity. But how did AlphaGo do it? Well, we'll find out in today's episode. How does Google DeepMind's AlphaGo work? First, let's take a look at what everyone is talking about. What exactly is AlphaGo? To understand that, let's step back and explore some history. In 2014, DeepMind created an AI program called Chess2Go, which learned how to play chess by analyzing millions of games online.
Yeah, the program was able to beat a top-level chess engine, but it still wasn't good enough to beat a human grandmaster.
However, 2 years later, DeepMind developed an improved version of the program called AlphaGo, which used a technique known as deep reinforcement learning to learn how to play the board game Go. This time, AlphaGo was able to defeat a human champion named Lee Sedol, who was widely regarded as the best player in the world. So how did this happen? Well, it all boils down to one simple concept: data. AlphaGo was trained on an enormous amount of data, which allowed it to learn the complexities of the game and develop its own strategies. In total, the team at DeepMind collected over 3 million human games of Go and fed them to AlphaGo. Additionally, they also gave it the ability to play against itself, which enabled it to learn from its own mistakes and successes. This process allowed AlphaGo to gradually improve its skills until it was able to beat a human champion. Now that we know what AlphaGo is, let's take a closer look at how it works. AlphaGo uses a technique known as deep reinforcement learning, which involves an agent learning how to perform a task in an environment through trial and error. The agent is rewarded when it takes actions that result in a positive outcome and punished when it takes actions that result in a negative outcome. Over time, the agent learns to maximize its rewards by taking actions that lead to the most favorable outcomes. In the case of AlphaGo, the agent is the program itself, and the environment is the virtual Go board. When AlphaGo plays a move, it receives feedback in the form of a reward or penalty. If the move leads to a winning position, it gets a large reward. If it leads to a losing position, it gets a large penalty. If it doesn't change the overall evaluation of the board significantly, it gets a small reward. Using this feedback, AlphaGo is able to learn which moves are more likely to lead to positive outcomes and refine its strategy accordingly. In addition to reinforcement learning, AlphaGo also uses a technique known as Monte Carlo tree search to select its moves. This technique involves simulating possible future moves and evaluating their outcomes in order to select the most promising move. By combining reinforcement learning with Monte Carlo tree search, AlphaGo is able to select the best moves based on both its own experience and an evaluation of possible future outcomes. AlphaGo's training process involves several steps. First, the program is fed data from millions of human games of Go. It uses this data to learn the basic rules of the game and understand how pieces move and interact. Once it has a good understanding of the rules, it can start playing against itself. As it plays more and more games against itself, it starts to develop its own strategies and learn from its own mistakes. The program is constantly being evaluated, and the best performing versions are saved and used for further training. This process is repeated until the program is able to beat a human champion. There are 4 main components to AlphaGo: the policy network, the value network, the selection network, and the training process. The policy network is responsible for deciding which move to make on the board. It takes the current state of the board as input and outputs a probability distribution over the possible moves. The value network estimates the value of a given board position. It takes the current state of the board as input and outputs a single value between 1 and -1. The selection network selects the move to make based on the output of the policy and value networks. It takes the probability distribution and the value estimate as input and outputs the move with the highest probability. The training process updates the parameters of the 3 networks based on the feedback from the game. If the move leads to a win, policy and value networks are updated to increase the probability of making that move in the future. If the move leads to a loss, the networks are updated to decrease the probability of making that move in the future. When AlphaGo was first released, it caused quite a stir in the AI community and beyond. Many experts were skeptical that a computer program could ever beat a human at Go, but AlphaGo proved them wrong. Its victory over Lee Sedol was seen as a major milestone in the field of AI research, and it showed that machines can master complex tasks that require human intelligence. One of the reasons why AlphaGo was such a big deal was because Go is a notoriously difficult game for computers to master. Unlike chess, where there are only a finite number of possible moves at any given time, Go has an almost infinite number of possible moves. Additionally, Go requires a lot of intuition and creativity, making it even more challenging for machines to master. Despite these challenges, AlphaGo was able to learn the complexities of the game and defeat a human champion. The success of AlphaGo has led to a lot of interest in applying deep reinforcement learning to other domains. For example, researchers are now using deep reinforcement learning to develop AI programs that can play video games, control robots, and even drive cars. AlphaGo has also inspired a lot of work on improving and extending its techniques. For example, AlphaGo Zero is a newer version of the program that was trained from scratch without any human data and was able to reach a superhuman level of play. One of the most interesting aspects of AlphaGo is the way it approaches the game. Unlike many previous computer programs that focused on brute force and calculation, AlphaGo uses a more intuitive and creative approach. It looks ahead to try to anticipate its opponent's moves, and it tries to find the best response to those moves. This approach has been highly effective and has allowed AlphaGo to achieve superhuman levels of play. Another interesting aspect of AlphaGo is the way it handles uncertainty. In Go, there is a lot of uncertainty involved in the game. Players have to deal with incomplete information and unexpected moves from their opponents. AlphaGo is able to handle this uncertainty by using a technique called Monte Carlo tree search, which allows it to simulate possible future moves and evaluate their outcomes. This allows AlphaGo to make more informed decisions and reduces the impact of unexpected moves from its opponents. AlphaGo has had a profound impact on the field of artificial intelligence and has inspired a lot of research and development in the area of deep reinforcement learning. Its success has shown that machines can master complex tasks that require human intelligence and intuition. And it has opened up new possibilities for the use of AI in a wide range of domains. I hope you enjoyed our exploration of Google DeepMind's AlphaGo. If you liked this video, please remember to give it a thumbs up and share it with your friends. And if you haven't already, please subscribe to stay up to date on all our latest content. Thanks for watching, and we'll see you in the next one.